Can you hear me? Hello? Okay, so I think I'll wait for a couple of minutes. I think there are only two of you. So we will start at, let's say, 5:05. Okay, so we will start at 5. Okay, so I think we can start. It's 5:05. So, welcome back. So, my name is Achinkya, and so today we'll have one problem session on the material which was covered in week 3. So, mainly there are two algorithms for finding minimum spanning tree. So, one is Kruskal's algorithm and the other is Prim's algorithm. Okay. So, what we will do is we'll see a number of questions on both the algorithms. So, before I get into questions, we'll apply the algorithm on one example so that you can remember what was the algorithm for both Kruskal and Prims, and then we'll look at the question on it. Okay, so the pattern of this session will be that I will write the question down in front of you, and you can sort of take couple of minutes or how much time you want to solve the problem. Let's say I'll give you couple of minutes, and then once anyone has any idea, we can discuss that idea, and after a while I'll give you the solution. I'll write it down and explain it to you. Okay, so okay, before I start, just give a plus one so that you can hear my voice, and second is you can see the shared screen so that I will know that you can see and hear me. Okay, so I think you can see. Okay, so let me start with what is called Kruskal's algorithm. So I'll give you a graph, which is a weighted graph. So there will be weights on the edges. It will be positive integral weights. And what you have to do is you have to run the Kruskal's algorithm iteration by iteration and find a minimum spanning tree. Okay, so let me write down the problem. Meanwhile, you can start thinking about it. So what you have to do is run Kruskal's algorithm. So Kruskal's Kruskal's algorithm and find a minimum spanning tree of the following graph G, of the following graph. Okay, so now let me draw the graph. So let's say you have A here, B, D, then C, E, H, F, and let's say some vertex Z, and you have weight 1, 2, 2, then there is 3, 3, 6, 7, 6, 8, 8, 9, 5, 4, and 4. Okay, so here is a graph G. So you can see that I have a weighted graph G. That means there is a weight on the edges. Okay, so what you can do is run Kruskal's algorithm and give me the value of minimum spanning tree. And then once you have tried it, we will all together will solve this problem. Like we'll run Kruskal's algorithm together on this problem. Okay, so you can take a minute and try on your own. Okay, so once anyone has any answer or idea, you can let me know, or you can even type in the chat whatever your answer is, and then we'll see if it is correct. Uh, so does anyone have any idea, or if you want more time to think, let me know so that I can proceed accordingly.
So we will select the edge having the minimum weight,
Hmm.
and then we keep on selecting. I mean, so better we sort the edges in the increasing order of their weights, and then we keep on adding the edges if they do not form a cycle.
Okay.
And yeah, and finally whatever we got would be the MST.
Okay, okay. Yeah, so this is a Kruskal's algorithm. So we'll start and let's apply this algorithm together on this example so that you will remember what was the algorithm and how to use it. Okay, so the first step in Kruskal's algorithm is to sort the edges according to their weight in non-decreasing order, right? So if there are, so for example, what is the edge with the smallest weight here? Can you tell me?
Yes, so that is one. But I hope that this algorithm will work fine even for the negative weights also. There is no
Yeah,
issue
yeah.
because yeah, eventually cycle is not going to form, so that won't be an issue.
Yes, yes, yes. Okay, so let's do this together. So first step is to sort the edges in non-decreasing order of their weight. So let's start. So the first edge that we will add is AB because the weight is 1. Now there are two edges, BD and B. Okay, so there is only one edge of weight 2, so we'll add that one. Okay, no, so there are two edges, sorry. So there is an edge BD and there is an edge AC, right? So there are two edges with the same weight. So what you can do is you can arbitrarily choose one edge out of these two. Okay, so right now I have chosen BD and then I will add AC. Okay, so the weight is 1, 2, 2. Now what is the next weight that is possible? 3. So again, so you have how many edges? 1, 2, which have weight 3. So then I will add those edges arbitrarily. So BC is one of the edge and BE is one of the edge. Okay. Then what is the next weight possible? That is 4. So DE and DH. So DE and DH. Okay. Then once 4 is over, next a weight possible is 5 and I can see only one edge, that is EH. Then I can see that there is an H with weight 6. So there are two. So CE and CF. You can pick them in any order you want. So CE, CF. And finally, you have 7, 8, 9. EF. So EF is one H. FH, FH, and FZ. Right? So this is a non-decreasing order of their weight, right? So the edge with least weight is AB, and we have started there, and then we have just sorted the edges in non-decreasing order of their weight. Now, what Kruskal's algorithm tells you is that you start putting these edges one by one in the minimum spanning tree. Okay, and you add the edge only if it doesn't form cycle with its previous edges. Okay, so let's do this. So let me first add the vertices here and then we'll add the edges accordingly. So let's say A, B, D, C, E, H, F, and Z, right? So there are 8 vertices here available. So how many edges will be there in minimum spanning tree? Can anyone tell me?
N minus 1 plus
Yes. So
1
n
plus
here
1.
is, huh. So you're right. So if I have a graph on n vertices, I have to add n minus 1 edges, right? So here n is 8. So I have to add 6 edges. So I'll start with the first edge AB. Clearly there is no cycle formed, so I can add AB edge in my minimum spanning tree. Then the next edge here, okay, so let me say this AB is done. Now next edge is BD, so I can add that because it is not forming any cycle, so I'll add BD. So BD is also done. Now next edge is AC. Again, it is not forming any cycle, so I can add AC with weight 2. So AC is also done. Now the next edge is BC. So can I add the age BC in this minimum spanning tree?
No.
No, right? Because simply because the I have added three ages until now, right? So AB, BD, and AC. So I have added three edges. So the new edge that is next in the sequence, if I add that and there is a cycle, then clearly that edge should not be in my minimum spanning tree, because I mean we are constructing a tree, right? So the trees are acyclic, so there should not be a tree. So BC edge cannot be there. So I will sort of put a cross sign below it. So BC is done. Next is BE. BE we can add. There is no cycle, so the weight of BE is 3. So then BE is also done. Now next is DE. Again the same thing. DE cannot be added because it forms a cycle DBE. So I have to remove DE. So I mean we cannot add it to the solution. The next is DH. I can add because there is no H, so I'll add this H DH, right? Next is so okay, DH is done. Can I add EH? No, because if I add EH here like this, uh, hello, can you hear me?
Yes, yes.
Yes,
Okay,
sir.
so somehow I think the H was not appearing. Okay, so I cannot add the H EH because it is forming a cycle BDHE. So I have to remove it. So let me just remove this H. Uh, then I will look at the next stage. So EH is not possible. So let me just sort of put a cross here. EH is not possible. Next age is CE. C is also not possible because it is forming a cycle here. CABEC. So C is not possible. CF. Yes, CF we can add because you can see there is no cycle. So CF is of size 6. And then okay, so CF is done. I have added it. Then next is EF. Again there's a cycle of length 5, so I cannot add it, so I'll just put a cross sign here. Next is FH. FH cannot be also added because there's a cycle, so FH will also be removed. And finally FZ, right? So this is FZ. FZ can be added because it is of so it is not forming any cycle. So the let's add few edges. Okay, so the so this is a minimum spanning tree. So let's see what is the weight. So the weight of this minimum spanning tree, so let's call it T. I'm just giving it a name. So what is the weight of this spanning tree? So 15, 16, 17, 18, 20, 23, 27. So is this correct? The weight is 27, right?
Yes.
Okay, so this is a very simple example of how you can run Kruskal's algorithm. So the summary is to sort the edges in non-decreasing order of their weight and choose the first one you add.
So why we say non-decreasing? It is we can say it is an increasing order also.
No. So the reason, so for example, let's take this example. So AB has weight 1, BD has weight 2, and AC also has weight 2. And let's say BC is 3. So if you see, I have put the edges in the order, but this is not an increasing order, right? So the first weight is 1, and then the next weight is increasing to 2. The third weight is not increasing, it is again 2. That's why I'm saying non-decreasing.
Okay.
This, yeah. So okay, so basically I mean if the age weights are distinct then it would be increasing order, but there's a chance um, that weights could repeat itself. So for safety I just said non-decreasing. Okay, so this is a simple example. So if you have understood this example and the algorithm, put +1. If there is any doubt in this example or the algorithm, please ask.
Someone said it is for non-decreasing order. What does it mean?
Non-decreasing means if you look at the
So no, the non-decreasing means sorry. Someone said it is for non-negative also. Sorry, non-negative. Sorry, negative weight also.
yeah, so if you so you can also put on negative weights. I mean there is no restriction on the weights of the edges. So if you see here I have put like only positive integers. You can also put zero point 0.5 root 2 -1 anything you want, right? So the weights are here in this case are positive, so you can also take negative and there will be no problem. So you just have to put the edges in non-decreasing order and run the algorithm. It will return you the right answer.
And what about applying the Kruskal's algorithm for the directed graphs? And do I mean, so does there any mean of or any relevance of computing the MSTs for the directed graphs?
Okay, so first of all, when you talk about directed graphs, it is very important to sort of see the notion of tree in undirected graphs makes sense. What when I say it is a spanning tree on undirected graph, what does that mean? Is minimum number of edges I will add with minimum weight so that every vertex has a path to every other vertex, right? So if you see here in this sort of a tree here I have drawn, this is a minimum spanning tree. And what is the significance? Like, what does it mean? I have to add minimum number of edges with minimum weight so that every vertex is reachable to every other vertex. Now, when we go to directed graphs, the notion of path is very different. I mean, so if you sort of have this sort of directed graph, let's say A, B, C, ideally there are two edges and three vertices, so there should be a tree. But it doesn't make any sense when I say spanning tree in directed graph, at least for now, because I cannot go from C to A, right? So that's why this notion of minimum spanning tree is only restricted to undirected graphs, right? So you'll have to first define what do you mean by minimum spanning tree on directed graphs. Once that is defined, you can sort of find a different algorithm or modify this one. But defining that itself takes some effort, and I also don't know if there is a notion of minimum spanning tree in directed graphs. So was that helpful?
Yeah, thanks.
Okay, okay, so now let's do some questions on this algorithm. So so okay, so let me write down the question, and this question has to do with minimum spanning tree. Okay, so let me write down. So let's say you have a graph G, and so vertex set is V and edge set is E, and this is an undirected graph. So undirected graph and connected. So the graph is connected graph having more than mod V of G minus 1 edges. So the graph contains V of G many vertices, and the number of edges in this particular graph G is more than V of G minus 1, and G has a unique heaviest wedge. Heaviest edge E. So let's denote it by E. So the question is then E cannot be part of a minimum spanning tree. So this question is true or false. So A option is true, B option is false. So okay, so here is a question. So let me repeat and I'll let you think about it for a minute. So you have given a graph G. There are two things. First of all, the graph is undirected, and second, it is a connected graph. These two things are very important when you have to talk about minimum spanning tree. Okay, you cannot have a minimum spanning tree on disconnected graphs, right? Because tree minimum spanning tree by definition means there is a tree as a subgraph which sort of is connected and there are no cycles. If the graph itself is disconnected, then you cannot have a minimum spanning tree. Okay, so these two things are given, and there is one more thing, that G, graph G, has a unique heaviest edge. So if you sort the um, edges in, let's say, non-decreasing order of their weight, the edge with highest order is unique. That means there are no there is no more than one edge with the same weight and which is the highest weight. So the question is it necessary that E cannot be part of a minimum spanning tree? So this is a true false question, you can think. If you think this is true, you have to sort of give me a reason why. And if you think it is false, then you have to construct a counter example and tell me why that example works, sort of contradicts this question.
So I think it is true because we would be arranging the edges in the increasing order of their weights, and moreover, the given graph is a connected one, so we can move. So we can move from a vertex to any other vertex. And since in this algorithm we would be following a greedy kind of the strategy,
Mhm.
so if we find something which seems the better at the moment, then definitely we'll go for it, irrespective of whether it is leading to something which is globally optimal or not. So what would happen that since we have Vg minus one number of the edges and we require only Vg minus one number of the edges, so first Vg minus one number of the edges will get selected. And since E is the heaviest weight and this is the only edge which has the maximum weight, so this will left at the end and the inclusion of this edge most probably will form a cycle. So I think it is true.
Okay, so does anyone have any different answer, or
I
you guys
think it
agree
is.
with this?
I think it is false
Okay, why?
because if you have if the heaviest edge is connecting the connector vertex with everyone, then it is the only edge that can connect the vertex. So it has to be in the three.
Yes, yes. So I think you have a right idea. So the answer to this question is in fact false. Okay, it is surprising, but let me explain. So when we talk about Kruskal's algorithm, what we do is we put the edges in non-decreasing order of their weight, right? And then we have to choose mod v of g minus 1 edges and add it to minimum spanning tree. But what is the situation, or like what could happen is when I'm adding edges, up to some point I'm adding, and let's say there are of very small weight, so I add, and after one point it could happen that any edge that I added is giving me a cycle, and you just went this way till the end, and the heaviest edge you could add, right? So let me give a example, sorry, let me give an example, counter example for this, and then you can easily see. So let me draw a graph, and you can see. So let me say, so let me write down names: A, B, C, D, E. So if you have, let's say, weight 1, 2, 3, 4, and let's say the weight here is 1000. Okay, so now if you look at this example, and even okay, so let's look at this example and try to run Kruskal's algorithm on this one together, and we'll see what is going on exactly and why is the heaviest edge is part of the minimum spanning tree, despite the graph contains more than v minus 1 edges. Okay, so let's first thing is always sorting the edges. So first edge is AB because it is of minimum weight, then AD, then BE, then DE, and then BC. Okay, so there are five edges. I have put them in this case, it's the increasing order. Now, let's look at the minimum spanning tree. So let me first put the vertices. Okay, so the first edge is AB. I can add. Weight is 1, no problem. Next is AD. I can add. Weight is 2. There is no problem because there is no cycle. Next edge is BE. So I can add, there is no problem. Now I have two edges left and I have to pick one because I have only picked three edges and I have to pick total four edges because there are five vertices. Now the problem is I cannot add DE edge to this minimum spanning tree according to Kruskal's algorithm, right? Because there's a cycle forming when I add the DE edge. So the only option I have to add is BC, which is of weight 1000. Now you can see that 1000 was the unique heaviest weight edge in my graph G, and any minimum spanning tree that you can build here for this graph, it is containing that edge. Okay, so if you have understood this question, please put +1. If you have not, please ask me questions so that I can clear the doubts. Okay, thank you. Yes, so I think you have understood this question. So now let me give you one more question. Um, Now, before jumping into a lot of problems, so let me also tell you the other algorithm, which is Prim's algorithm. So let me just write it down. The question. So I'll give you an example, and we will all together look at the graph and run Prim's algorithm on it and see how to construct minimum spanning tree using Prim's algorithm. Okay, so run Prim's algorithm on the following graph, starting with vertex A. Okay, so let me give you the graph. So I have A, C, B, F, G, and D, H, E. So weights are 3, 5, 1, 2, 3, 4, 3, 4, 6, 6, 6, 5, and 4. Okay, so I think I have. Wait, so let me show you the question. So here is a wait. There is a doubt, sir. If some more edges have weight 1,000, then it will be unique also. No, so the definition when I say unique, that means there is only one edge of heaviest weight. Now the heaviest weight here was 1,000, so there cannot be any other edge with the same weight, right? Because then it is not unique. There are two of them. I hope that answers your question. So the answer is there cannot be more than one edge with heaviest weight in this problem. Okay, I'm talking about the last problem because the problem said that I have unique edge with heaviest weight. Unique means there is only one. Okay, okay, I think that's clear. Okay, so the next question is to run Prim's algorithm on the okay, so run Prim's algorithm on the following graph. So here is a graph G, and you have to not only find a minimum spanning tree, you have to run the Prim's algorithm starting with vertex A, and then iteration by iteration you have to construct a minimum spanning tree. And once you have constructed it, please let me know. So you can tell me what is the weight of the minimum spanning tree, and then we'll all of us together will apply Prim's algorithm on this example. Uh, so does anyone have the weight of minimum spanning tree in this case? Okay, so I think okay, it's okay. So let's work it out together. So what is the Prim's algorithm? So it start with vertex A, right? So we have one vertex A on this side, and we put all the other vertices on the other side, and we see the cut edges going across. So let me write it down, and it will be clear. So what I'm
Sir,
saying
is it
is,
25?
let me check once. Yes, yes, you're right. It is 25. Yes, yes, nice. Uh, okay, so let's start together and see how we can calculate the weight and also the MST together. Okay, so what is the Prim's algorithm? It puts a vertex on one side and it puts the other vertices on the other side. Let's say C, D, H, B. Okay, let me just do B. Then we have E, F, G, E, F, G. So this is called a cut of the graph G. By cut, I mean partitioning the vertices into two parts. I put A on one side and all the other vertices on the other side. Note that the Prim's algorithm sort of needs a starting vertex so that it has the initial cut. You can pick any vertex, but just because the question specifying which vertex I have to start with, I'm starting with A and all the other vertices are one side. Now I have to look at the cut edges according to this cut. What do I mean by cut edges? The edges that have one endpoint A and the other endpoint here on the right side. So in this partition, right? So let's see what edges are here, which are cut edges. So you can see AD is an edge with weight 1, and then there is okay, AD is an edge that have one endpoint on A and the other endpoint on the other side. So AD is an uh, cut edge. So there is one more AC, which is 2. Now you can see the rest of the edges in my graph G are not cut edges because they have both the endpoints on the right hand side, right? So the only cut edges are AC and AD. Now what Prim's algorithm says is that once you have constructed this cut, you pick the edge, you pick an edge with smallest weight. Okay. So in this case, what is the edge with smallest weight? It is AC, right? Uh,
No, it's a
AD, yes. So what I will do is I will add that age AD in my minimum spanning tree. So let me draw here. So I have this AD on one side. The weight is 1. And again, what I'll do is I'll put the rest of the vertices in this box. What is this? C, H, B, E, F, and G. Okay. So now again, this is like a second iteration. Again, I have to look at the edges, which are cut edges. But see, the cut has changed. Before I had A on one side and the rest of the vertices on the other. So this was, you can say, one cut. Once you have added the edge AD in my minimum spanning tree, you have a different cut. So AD on one side and the rest of the vertices on the other. So this is a new cut. So let's say this is a new cut. So this is a second iteration. Second iteration. So this was first iteration. Okay, so let's see what are the cut edges with respect to this new cut that I have drawn. So I have AD on one side. So there are, I can see three edges. So one is AC is an edge of weight 2. So sort of this is the cut, right? You can see that AD I have put on one side and the rest of the on the other. So this way it will be easier to see. So let me just remove this because it will change every time. So then I have DC. So let's say DC of weight how much 3, and then I had one more edge, right? DH. DH. So DH is of size 3. So again, so this is a new cut and there are three edges: AC, DH, and DC. Again, the Prim's algorithm says that pick the one with minimum weight. So here the edge with minimum weight is AC. So I'll pick AC here. I had first choose AD here. So let's see now. Let's construct the new cut. A, C, and then I have D. AD is 1, AC is 2, and let's put the other vertices on one side. So this is done. So this is now third iteration of the Prim's algorithm. So let me just write down the other side. H, B, F, E, and G. Okay, let's find out the cut edges. Uh, so let me go here. So now I have C inside it. So now my new cut looks like this, right? So D, C, and A on one side, and H, B, E, F, G on one side. So I can see there are three edges, D, H. So let me draw. Somehow I think that is not getting erased. Plus, okay. So DH is one weight, sorry, one H with weight 3. Then I have A. No, then what is the next stage? CH.
CH.
Yeah. So CH have weight how much? 3. And then finally CB.
CB.
Yeah. CB. Yes. So I have CH, CB, and DH. So I have made a new cut, and there are three crossing edges as you have said. And what is the edge with minimum weight? You have to pick according to Prim's algorithm. So let's see. So sorry, just a minute. So I will add ch edge to my minimum spanning tree. So let me draw a new page. So H, C, A, D on one side, and then B, F, E, G on one side, and CH is added. So what is the weight of CH? 3. Then CA was 2 and AD was 1. So this is my fourth cut in my fourth iteration. Fourth iteration. So let's see what are the edges that are going across. So now, so let me just draw because I think you cannot see the main graph. So let's say HE is an cross edge, HF is an cross edge, and then there is HB. HB is also an cross edge. So HE, HF, and HB. HB, HF, and HE. Okay, so these are the three edges which are cross edges. So let's look at the weight. HB has weight 4. So 4. HF has weight 4. So I'll put 4. And HE has weight 5. Now, as you can see, there are two edges with minimum weight, which is HF and HB. Right, and HE has larger weight, so it doesn't matter which one you pick. You just arbitrarily pick which one you like. So let's say I pick HB here. So now I will have HB in my minimum spanning tree, and the rest of the edges are here. So D, the weight was 4. So 4, then 3, then 2, then 1, and let's put the rest of the vertices on one side. So I have put B here. So now F, E, G. So this is my fifth iteration. And let's look at the cross edges. So let me see. So I have F, E, G on one side. So H, E is an cross edge. Uh, H, F is an cross edge. And which is it? B, F is also an cross edge. Okay. So BF has weight 6. BF has 6. HF has 4. And HE has 5. Okay, so again, so I have three edges and the minimum. Okay, so let me write down what are they. HE, HF. Sir, CB also include in fourth cut. So let me go back. Okay, so CB. Oh, okay, 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 okay. So I think he is right. So here is said CB also should be in the weight. Wait, so this is right. So I forgot one edge. So here CB is 3. Okay, thanks. Thank you. Yes, yes. So this is C. B is also there. Okay, so now let me write down these things again because I made a mistake. So let me just rub this. Okay, so let's go back to fourth iteration. So he's right. So CB was the age with minimum weight. So let me write C, uh, B, H, A, and D. Okay, so yes, sorry. So I have added B, so I'm left with F, E, and G. So CH had weight 3, CB had weight 3, and then this is 2 and this is 1. Okay, so let's see what are the cross edges for this fifth iteration. Okay, so let me see the graph. So I have HE as an cross edge, which is of weight 5. Then I have HF, which is of weight 4. I have what is the next? BF. BF is here, which is of weight 6. Right. So this is the fifth iteration. And what is the age that I will add to my minimum spanning tree? Well, HF. Right. This is the smaller one. So let's say HF. So let's add. So HF B. HF had weight 4. This is 4. Then this is 3. Then C is 3. Then A and D. So this is 2. This is 1. And again, I will construct the sixth iteration. So this is a new cut again. So, okay. So what are the two vertices left? This is just E and G. Sir, CB is 3. Oh, sorry. CB is 3. Yes. Nice. CB is 3. So this is correct, right? So can anyone confirm so that I won't make any new mistake? Okay. Yes. Thanks. Uh, Now, what are the edges which are cross edges? So I have EG on one side. So I can see that there is EF, which is of weight 5. Then I have EH, which is of weight 5. EH, and then there is GE. So G is not there. GF. Okay, so let me draw GF. So GF is how much? GF is 6. So I have HE, FE, and GF, right? So again, sorry. So let me just draw a new cut. So this is sixth iteration is done. So I have moved down to seventh iteration. So I have F. So I'm adding HE. So HE. Then this is C, B. Then this is A. This is D. So HF is 4. HE was 5. Then HC was 3. CB was 3. CA 2, 1. So I have moved E. So now I'm only left with G. Okay. So what are the edges which are going across? GE and GF. GE and GF. And GE has weight 6. Sorry, GE has weight 6 and GF also has weight 6. So no problem. Uh, Now you can pick any edge. So I will just write it here. So I'll take, let's say, GF. So this is my um, what is it called? Minimum spanning tree. So let's say weight. How much weight does this minimum spanning tree have? So weight of T. Okay. So 10, 15, 21, 24, 25. Yes. So someone said 25, which was correct. So the minimum spanning tree has weight 25. So here is a question. So how many iterations do I have to run in order to construct a minimum spanning tree using Prim's algorithm if there are n vertices in my graph G? Okay, so let me repeat the question. So the question is, as you just saw, I ran Prim's algorithm on the graph G. So I wrote first iteration you get one cut, second iteration you get cut. So there are a lot of iterations where Prim's algorithm is adding edges to my graph G. So how many times I have to run these iterations in order to get a minimum spanning tree? Okay, so I think
N number of the times or n minus 1?
yes, so I'll have to run n minus 1 times because in the first iteration I'm adding one edge, in the second iteration I'm adding second edge, and the minimum spanning tree contains n minus 1 edges, so it is n minus 1 times. Okay, so I think someone wrote yes, this is correct, n minus 1 times. Okay, so this is simple. So now let me give you a question and we'll see. Um, okay, so okay, so let me write down the question. Let's say question. So if T is a minimum spanning tree of a weighted graph G, then the UV path in T is a minimum weight UV path in G. So this is again true or false. So, okay, so let me explain you the question. You can take a minute and think. So this is also very interesting question. So let's say you have some graph G and then you ran your Kruskal's algorithm or Prim's algorithm, one of these two, and calculated a minimum spanning tree or some other algorithm for that matter, any algorithm you run, and you got a minimum spanning tree T of the graph G. Now, what you can, the question is asking, so in the original graph, you have two vertices, let's say U, V. Now, in the original graph, I have a shortest path from U to V of minimum weight, right? So, minimum weight path UV is there in my original graph G because the input graph is connected. Now, you constructed a minimum spanning tree. So, you have only used n minus 1 edges from the graph G, and now you have a minimum spanning tree which is a subgraph, right? A minimum spanning tree is a subgraph of G. Now in this new spanning tree, you also have a path UV because tree is connected graph. So any two vertices are connected. So there is a UV path. So this is also weighted path. So now the question is the weight of this UV path in my minimum spanning tree equal to a minimum weight UV path in G, right? So if you have understood the question, please think about it, and if there is some question or you have doubt in the question, please ask. Sir, please give some example. Okay, so let's see. Say three. Okay, so let's say this is your graph G, right? And so there are a lot of spanning trees, so let's calculate one minimum spanning tree. So let's say 1, 3, 4. So let's say A, B, C, and D. So this is a minimum spanning tree of the graph next to this graph G. Now, what is this question asking is you have some graph G and you calculated its minimum spanning tree of this graph G. Now, in the original graph, let's say here you took two arbitrary vertices. So let's say A and you picked D. Okay. Now, in the original graph, what is the shortest path from A to D? What is the least weight path from A to D? Can anyone tell me? So I'm assuming you know what is the distance between A and D in
Yeah.
the
So from A to D, and then so its value is 5.
huh yes. So he is right. So he said the shortest path from A to D in the graph G. Okay, in the graph G is 5 because what I can do is I can go from A to C and C to D, right? This is 5. So there are all different paths also which uses two edges. So for example, AB and then BD. But the weight here is 6. So the shortest path or the distance of A and D in my graph G is 5, right? I hope this distance between two vertices in a weighted graph is clear. Now the question is asking, it is true that the distance between A and D in graph G is 5. Will the distance between A and D in my minimum spanning tree of this graph G will also be 5? Is it always true that this shortest paths, the weighted shortest paths will be of equal length if I look at it in G or if I look at it in T? Uh, so here AB is 3, this is 1, this is 4. So you can think for a minute and tell me.
No, because if we are going to apply Prim's algorithm, it will go from AC, then from AB, then to AB. So,
Wait, no. So if you apply Prim's algorithm, okay, so let's apply Prim's algorithm and look at this graph G. So what is the first edge Prim's algorithm will add? It will add AC, right?
yes.
And then it will add AB because this is the crossing edge AB, BC, and CD. So there are three crossing edges, but AB is the shortest, so it will add AB, and then it will finally add CD. So in this special case that I'm talking, the distance between AD is also 5. So for this specific example, distance between AD, whether I look at in graph G or whether I look at in graph T is the minimum spanning tree of my graph G. Are these two distances equal for all pairs of vertices?
So I think this is true because whenever we select an edge in a cut, whenever we select an edge crossing the cut, we take the one which is the lightest one. So yeah, so and in this greedy approach, what would happen that uh, we will definitely be having we would definitely be having the shortest path in between any pair of the vertices in the
Uh,
instant.
okay, so this is one answer. So what about others? Do you think this is true, or I mean, do you agree with him, or do you have a
Uh,
different answer?
like if we, in some cases, if we have one option, like we have two ways to go, and if, let's assume that one edge is lesser than the other, which will be true mostly, but maybe after in the larger one, maybe after, in the next part, the length of the next edge
Mhm.
would be so less that it will make its weightless and to go to you, then it will fall. Matlab,
So
I mean, his argument will
I
fall.
understand what you are trying to say, but can you
Yes,
give me
yes.
a very simple example where what you are saying will happen? Very simple example. I think the example is just three vertices. So okay, so
Yes, I was.
huh.
I
So
mean,
for others, so what he's saying is it is false, and surprisingly in this case as well, the answer is false. Now let's see why. I think so. Someone said that the way Prim's algorithm chooses the edges, it chooses the edge in the cut which is going across of minimum weight. So if I have to go from A to somewhere, it will sort of use these edges with minimum weight. But that doesn't happen exactly in minimum spanning tree. Okay, so let's see. So let me give you an example, and it is like one line example, so you can see. So let's say you have a triangle. Weight here is 3, then it is 2 here, 2 here. So this is U, this is V, let's say W and P. So here is my graph G. So you can quickly see, and so what are the two edges that will go to minimum spanning tree?
Remove three words, three edge wala tree.
Yes, yes, you are right. So minimum spanning tree is this U, W, V, 2, 2. Okay, now if you see the distance between U comma V in G was how much? Is how much here? 4. No, the distance between U and V in G is 3. Yes, so I think you are talking about the minimum spanning tree. So let me talk about that. So here the distance is 4 because there is only one path UWV. But in the original graph G, there was a better path UWV. Although, sorry, in the original graph, there was a better path UV, which is of weight 3. But when I go to minimum spanning tree, that edge got disconnected. I mean, removed from the graph G. And now I only have one path UWV. So the distance is now 4 in my minimum spanning tree. Okay, so the distance, minimum distance between two vertices can change when you go from graph G to a minimum spanning tree T. Okay, so if you have understood it, put +1. If you have any doubt in this example problem, please ask me.
So yes, but this certainly leads to a question mark on the correctness of the Prim's algorithm. So
So
how would we prove that this algorithm is going to work in every situation?
yeah, I think we'll get to one question where you will see that why Prim's algorithm work. So see, Prim's algorithm's job is to not is really not to maintain the distance between two vertices. The job is to globally connect everyone so that the total distance is in decrease, right? So
Yes.
right, I mean when I said total, there's a, I think it is not formal, but I think you can understand it. Its job is to connect all the vertices to each other so that the total weight is small. But while doing that, there could be two vertices whose path is small, but while joining everyone to each other, that path could be sort of gets bigger. Okay. Okay, so
And avoid cycle also in that.
yeah, there could be no the thing about cycle is that he said that you are taking only one edge in the, like the cut, so there won't be any cycle and you are picking the edge with minimum weight. But even after that, even if there is no cycle, it could go wrong. Okay. um,
Yes, and out of curiosity, I would like to ask one thing. And I vaguely remember a variation of the MST wherein the shortest distance among a subset of the vertices need to be maintained. And if I correctly remember, the name of the variation was the Stanners tree.
Steiner tree, yeah, yes. So Steiner
So,
tree is something different, but yes, yeah.
okay.
But okay, let's not deviate. I think let's stick to minimum spanning tree for now. Okay, so let me okay, so I think I see plus ones. Okay, so there is someone who is saying we will, sorry, UV is equal to 1. I don't understand the question. So the weight of the edge UV is 3. So the shortest path from U to V is 3 length. The length is not 1. Although I'm taking only one edge, I'm talking about a weighted graph. Okay. In weighted graphs, the distance between two vertices is not a path with minimum edges. The path with least weight is the shortest path between two vertices when I'm talking about weighted graphs. So the distance between U and V in the original graph G is 3. Okay, it is not 1, right? Yeah. And yes. So, okay. I think it's clear. So now let me go to a bit different question. So let me see. So, okay, so this question has to do with properties of minimum spanning tree. So let's do this. So here is a question. So which of the following is false in the case of a spanning tree of graph G. Okay, so this is a statement. This a tree that spans G, then it is a subgraph uh, of G. The third is it includes every vertex of G, and this is T. It can be either cyclic or uncyclic. Cyclic or acyclic. Okay, so here's a question. So you have given four options, and one of them is false. So you have to choose out of these four which one is false and tell me. And the ones which are right, you have to give me. Okay, so I think I already see a lot of answers. Yes, so you are right. So for others, please take your time. So I think a lot of you have already done it, but I just want everyone to think about it. So I'll wait for a minute so you can think.
Both Prims and Klusker, they give the same spanning tree.
Okay, so there's a question. Okay, so you are asking, does the Kruskal and Prim's algorithm always give a same minimum spanning tree? The answer is no. First of all, minimum spanning tree is not unique. The weight of minimum spanning tree is unique, but the minimum spanning tree itself can be different. So let me give an example before I proceed to question. So so let me think once. Just a minute. Let me just think. Okay, I think I can give you a relatively simple example. So let's say weight is 1 1 2 2 A B C D. Okay, so the question he has asked is whether these two algorithms always generate same minimum spanning tree. But before answering that question, I have to first explain that minimum spanning tree is not always unique. There could be lot of minimum spanning trees in for my graph G. So let me give an example with two minimum spanning trees, and then you can see. Okay, so so let me draw a minimum spanning tree. So here's a minimum spanning tree. So A B A B C 1 1 1 1 2. Sorry, this is A B C D. So if you see this example, this is my graph G, and let's say this is T1 and this is T2. So first you can see that T1 and T2 are two different minimum spanning trees because the tree T1 contains AC, which is missing in T2. T2 contains CD, which is missing in T1, right? So this is an evidence that minimum spanning trees are not unique. And also the answer to your question is also true. If you apply minimum spanning tree algorithm, Kruskal's and Prim's, it is possible that they generate uh, two different minimum spanning trees. In fact, the algorithm, if you think, remember Prim's algorithm, you have to start with one specific cut where you take one vertex on one side and all the other vertices on one side, right? So this is sort of the starting point of Prim's algorithm. If you change the initial vertex, then it could be possible that you are getting two different minimum spanning trees. Whatever is the output of that algorithm, it will always be a minimum spanning tree, but the answer will depend on which vertex you
Hello.
choose. Yes. You have any questions?
So what if the weights of all the edges are distinct?
Yes, yes, we'll get to that question. So that is, in fact, in my assignment. So we'll get to that. But before that, let me just add this. The algorithm, the Prim's algorithm, uh, or Kruskal's algorithm for that matter, they don't not necessarily create unique minimum spanning tree. Depending on the order, how you put the non-decreasing order in Kruskal's algorithm, and how you choose the first cut in Prim's algorithm, it matters, and it might generate two distinct uh, minimum spanning trees. Okay, and then I think you asked if, what if the weights are distinct. I'll get to that after this question, in fact. So let's do this question first. Okay, let me just drop this. Uh, so if you see, this question has nothing to do with the minimum spanning tree. Okay, it has only to do with spanning tree. So that is first observation. So let's see, what is a spanning tree? Well, it is any tree or any subgraph which contains all vertices of G, and there is no cycle, because I mean it is a tree, right? So first A option is correct. It is a tree that spans G. By spans, I mean all the vertices are there. Second, it is a subgraph of G. Well, yes, because I'm not adding any new edges to my graph G. I'm just deleting few edges. So this is a subgraph. Third is, it includes every vertex of G. This is true by definition. Um, I mean, a spanning tree always contains all the vertices. And finally, D part is incorrect, like a lot of many of you said, because by definition, tree is acyclic. It cannot be cyclic. Therefore, spanning tree also should be acyclic, and there should not be any cycle. So D option is wrong. So D option is wrong. A, B, C are correct. Okay. Okay, so let me move to the next question.
Sir, but in my question, what I
Uh,
asked, if now both will give the different spanning tree,
uh-huh.
so then how to select the algorithm then? Which is the best one?
Okay, so there are two answers. So let me first tell you that although the spanning tree returned by Kruskal's algorithm is different, it might be different from the um, minimum spanning tree given by Kruskal's algorithm, or like the two distinct. It is it will always be true that these two trees have equal weight. Okay, because both are minimum spanning trees. So it doesn't matter which answer you take. It doesn't matter which answer you take. Both of them will be minimum spanning trees. Now the question is, okay, although both of them are giving the same answer, which one will I pick first? Which algorithm is better? But to discuss what algorithm is better, I have to talk about the complexity of the algorithm, which is not really part of this course. So I'll not go into this. But those of you who know algorithms, you know this. These algorithms can be run in linear time. So based on the input of the algorithm, like if it is given in the linked list form or adjacency matrix, you have to decide. For those of you don't know algorithms, it doesn't matter. The answer is, you can pick any algorithm you want. The output of the algorithm will always be minimum spanning tree, whether it is Kruskal or Prim's. The spanning trees could be different, but the weights will be equal, and the weight will be minimum spanning tree. The weight will be equal to the minimum spanning tree weight. Okay. Okay. Now let me go to the next question. Okay. So let's see. So, oh, sorry. Question number. Okay. So consider an undirected graph G. So let's say I have undirected graph G with vertices A, B, C, D, E. Now, in this graph G, every edge has distinct weight. Every edge has distinct weight. Edge CD is edge with minimum weight. and age AB is age with maximum weight, then which of the following are true? So let me give you the first option. Every minimum spanning tree of G must contain CD. So let's go option by option because I think this is a long question, so it will be easier. So here is your first option. The question is it always true that given undirected graph G, which contains five vertices A, B, C, D, and E, there is a so all these edges in this graph have distinct weight. Uh, Distinct weight, I mean no two edges have same weight. Okay, this is one. Second is that this edge CD is edge with minimum weight, and we have also given that AB is edge with maximum weight. Now the question is that every is it true that every minimum spanning tree of G must always contain CD, right? So you can think for a minute. I'll be back. Just a minute. I'll get some water for me. So you can think. Okay, I'll be just back in a minute. Uh, yes. Hello. Yes, Simon. So let's see. There's a question and there is an answer. The answer. So one of you is saying this is true. Okay. Are the edge weights non-negative or can they be any integer? So for now, let's say all of them are positive integers. Let's not worry about non-negative, positive, anything.
CD
So
is CD is every in every because it is minimum, so it is the part of chemistry.
no. So here is the thing. So before you answer, let me just first let me explain this weight non-negative or here you can assume that all the way edge weights are positive. It doesn't really matter. And the second question I think is regarding uh, minimum sanitary. So the A option is saying whether you use Kruskal's algorithm, whether you use Prim's algorithm, or you can just somehow found a minimum spanning tree. Okay, it doesn't matter how the minimum spanning tree is constructed. The algorithm is irrelevant here. This question has nothing to do with the algorithm. You have a minimum spanning tree. That's it. It is not saying it is coming from Spruce algorithms or Prim's algorithm or some other. So we have any minimum spanning tree. And the question is that whether CD will always be part of that minimum spanning tree. Okay, so this is a question.
So the statement is true because if you use Kruskal algorithm to construct a MST, then it will contain the lowest minimum weightage. So so one of the MSTs has the minimum weightage. It has CD.
Okay.
So if let's say there is another MST that does not have CD,
Hmm.
then its total edge weight it has to be less than the one that contains CD
Hmm.
because the edge weights are unique. So it cannot be an MST.
Okay, so what you are saying is, he's saying, let's say, let's consider Kruskal's algorithm. What Kruskal's algorithm does, it um, what's it? Sorts the edges in non-decreasing order. Here, all the edge weights are distinct, so it will sort it in increasing order. And the Kruskal algorithms will always contain the edge CD in my minimum spanning tree, which is constructed by Kruskal's algorithm, right? What you said is you are starting with Kruskal's algorithm. But what if I asked you, okay, I'm not using Kruskal's algorithm, I'm using something else. I'm using some algorithm that I'm not telling you which one it is. Now, can you tell me that this age CD will always be there in the minimum spanning tree, which I have, and the minimum spanning tree is constructed by some different algorithm, okay? And you don't know what algorithm is that. Now, can you say something whether A is true or false, anything like this?
So minimum weight edge will always be the part of what you say MST, uh,
Okay.
even if you use any algorithm.
Okay, so you are saying it is true. Okay.
So,
Um.
because the weight of the minimum spanning tree would be unique. Therefore, if we don't have CD, then there would be something else, which would mean that, and because CD is minimum, it would mean that the replacement of it is more than it, which will make sure that its uniqueness is not maintained, which is a contradiction.
Yes, yes. Okay, so I think so your explanation is on the right track. But I will just make it a little bit formal. Okay, so for others, does there anyone is left who has any idea and hasn't discussed? So you can tell me now, because after this I'll give you a solution, which I think false.
Basically, basically it is a optimization problem MST. So optimization will start with the minimum. What I want to say.
Okay, so so Anupam, what if I remove this distinct weight condition? Will this still?
Then it is a false. Then it is a false because there must be something, some edges, okay, which you can do. But distinct, because of distinct, I am saying
Mhm.
that it is true.
Yes, okay. So I think there's someone who is also saying it is false. So the answer is true, no matter how you construct your MST. So I'll use this short form MST, okay? I think so you can just take it MST is minimum spanning tree. So doesn't matter how you construct MST, uh, it will always contain CD. So let's prove it, okay? Intuitively, a lot of you are on the right track. It is because of distinct weights, you can always add it. But what we have to do is we have to formally write the proof. uh, so let's see. So let me prove it to you that why this age will always be there, okay? So let's say proof. So this is a proof by contradiction, which means I will assume what is not true. So let's assume there exists there exists a minimum spanning tree, MST, minimum spanning tree T. So let's say I'm calling that tree T, such that this edge CD does not belong to edges of T. Okay. So what I have done is this. I have to prove this statement, right? And the proof should be formal. So I'm proving this by contradiction. So I have assumed. Okay. So uh, let's assume that you constructed some MSTT such that the edge CD is not there. Okay. Let's assume this, and we'll prove why this is not correct. So here is what I'll do. I'll take this tree T and I will construct another graph, let's say G1. So let's say G1, which will be T union CD. Okay. So I started with MSTT. which is a minimum spanning tree. And someone said, okay, CD may not be there. Why should it be there? CD, so let's assume that CD doesn't belong to E of t. So what I'll do is I will construct a graph G1. So I'll put all the edges from T to my graph G1. And along with that, I will also put CD. Okay. Now, when I had T as a graph, I mean, when I had MS tree, MST, uh, T, clearly the graph T is acyclic and connected. Why? Because it is a minimum spanning tree. So T is connected and acyclic, and number of edges in T is how much? Number of V of G minus 1. So till this point, is there any doubt?
No.
Okay, great. So let's say this is tree T, which is connected and acyclic, and I know the number of edges in T is exactly V of G minus 1 because by the definition you have seen. Now I have constructed a new graph G1, which is you take the tree T and then you add the edge CD. If I add edge CD to a tree T which contains V of G minus 1 edges, what would happen? What will happen? Like, can you observe something? If I add an edge to a tree which is a spanning tree, what will happen?
It
Will
becomes
will,
cyclic.
will it be tree again? Will it be tree? Uh,
No,
no. Why? Because any tree on n vertices must contain exactly n minus 1 edges. I already had n minus 1 edges in my tree T. I'm adding one more edge. That means there will be a cycle. Okay. This, sorry, this implies, this implies that the graph G1 will contain a cycle which contains edge CD, which contains the edge CD, right? Why CD should be there? Because before CD there was no cycle. After I added CD, now there's a cycle. That means CD should be there. Otherwise, that cycle would have been there before I add CD, right? So I have a cycle in G1 which contains the edge CD. Okay. Now, if you think I have a cycle in my graph G1 which contains CD. Okay, so let's say E1 prime, E2 prime, E3 prime, dot dot dot, some EL prime and CD are the edges in this cycle. Okay, right? So I said there is a cycle in G1 which contains CD. I don't know what edges it is containing. It could be anything. Just to write it down, I said, okay, let's say the edges are E1 prime, E2 prime, E3 prime, dot dot dot, EL prime, and then CD are the edges in this cycle. Now the question is, um, does there exist an edge in this sequence E1 prime, E2 prime, E3 prime, EL prime, which has weight more than CD? Or is it possible that all these edges have weight less than CD?
Can you repeat this question?
Okay, okay. So let me go back and explain you the entire argument. Here is the thing. I have to prove that no matter what tree, no matter what minimum spanning tree you have given, CD will always be there. So I am trying to show that this statement is true, that the A statement is true. To prove that statement A, I'm proving it by contradiction. What do I mean when I say proof by contradiction? You assume something which is not true. So let's assume there exists a minimum spanning tree T. So here, such that CD is not there. So I just assume, okay, somebody gave me a minimum spanning tree where CD is not there. Assuming this, I have to prove that this statement is false because it leads to a contradiction. So I'm sort of trying to construct the contradiction. Okay. So how do I construct it? So you start with the graph G1, which is T union CD, which is in this red box. So this is my graph G1 that I'm considering. Okay, so what do I know about this graph G1? This graph G1 is basically take the graph T, which is a tree, and add one more edge to it, right? T is a graph which is a tree. That means it is connected and acyclic and it contains all the vertices of my graph G, right? So the number of edges in T is exactly V of G minus 1. So this is a property of minimum spanning tree. And since I have assumed T is a minimum spanning tree, this property should be true, whichever in this circle. Now let's observe the some properties of this G1. Okay, uh, let's see. So I had a tree T. What happens when you add one more edge to tree? It There will be a cycle, right? So let me give an example. Uh, so let's say here is a tree on 1, 2, 3, 1, 2, 3, 4, 5, 6 vertices, okay, and 5 edges. Can you add an edge to this tree such that there is no cycle?
No, because in the tree, the path from a vertex to any other vertex is unique.
Yeah, exactly. That means no matter which two vertices I add an edge, so let's say I added between U and V, there was already a path between both of them. So there was this path between these two, right? And then I added one more edge. That means this is my cycle. That means when I added this edge uh, CD to my tree T, there will be a cycle, right? And that cycle will contain my edge CD because before adding CD there was no cycle. After adding CD there will be a cycle. So that cycle must contain CD. Okay. Now let's focus on that cycle. What is that cycle? What are the edges in it? So let's denote the edges in that cycle by E1 prime, E2 prime, E3 prime, EL prime, and this edge CD is also there, are the edges in this cycle, right? Now, what I know, all the edges in this cycle have distinct weight. This is given as part of my question. I had 5 vertices and all the edges were distinct. Edge weights were distinct. So here, when you look at weight of E1 prime is not equal to weight of E2 prime is not equal to weight of CD, right? None of these edges have equal weight, right? That means CD is the edge with minimum weight. So what I'll do is I will go to this set E1 prime, E2 prime, EL prime, and I'll choose the edge with maximum weight and I'll remove it. So what I'm saying is this. You had graph G1,
So
which
I have
is,
a query here that
yeah,
in this discussion, what are the endpoints of the edges even prime and then last one is EL prime, I guess. So I assume that the one of the endpoint of the even prime is a C, and one of the endpoint of the EL prime is a D, so that we would be fusing one of the connectivity and then we can proceed.
yeah. So basically what I'm saying is there was a C to D path in tree T, and then you added an edge CD, right? So there was a path from C to D in my tree T, and then you add one edge CD. That means there is a cycle. So this is an edge CD, and then there is E1 prime, E2 prime, EL prime like this.
Yes.
Yeah. Now what I'm saying is, let's say I took G1, which is my tree T union CD, and I'm constructing another tree. Let me call it T prime, which is T union CD. Sorry, just a minute. Oh, sorry, this was correct. Minus EL prime such that weight of EL prime is greater than or equal to weight of EI prime for all I, right? So what I did is this. So let's parse this. I took a cycle in the graph G1, and the graph G1 is T union CD. In this cycle, I assume there are edges E1 prime, E2 prime, E3 prime, there could be anything, EL prime, and there is an edge CD. I know this, there is an edge CD. Now in this cycle, CD is the edge with minimum weight. Similarly, there will be an edge with maximum weight, right? Because I mean, there will be some maximum because all edge weights are distinct. So for now, let's assume it is EL prime. EL prime is an edge with maximum weight in this cycle. Okay, then I'll construct another tree T prime. What it does is it takes T, it adds CD, and it removes EL prime, right? Now in this T prime, first observation is that T prime will be connected because I have removed an edge from a cycle. The graph cannot get disconnected, right? This is a simple observation. If you sort of imagine you have a graph and there's a cycle inside it, and you are removing an edge from the cycle, then the graph remains connected. And the number of edges is again E of G, sorry, V of G minus 1. Why there are V of G minus 1 edges? Well, what did I do? I took tree T, I added one edge and I removed one edge. So the total number of edges is still the same, which is V of G minus 1. That means T prime, this newly constructed T prime, which is this, is a tree and it is also connected, right? So now let's look at what is the weight of tree prime. Okay.
So is it necessary that every time we are going to remove EL only, or it could be any age in this path? Could be
No.
even prime for to
Uh,
prime or could be anything.
so I mean, for the sake of argument, you can choose any age to delete, doesn't matter because all of them have weight more than CD. But let's say I picked the one with maximum weight. Okay.
Okay.
Okay. When I say maximum weight, I mean maximum weight in this particular cycle I'm talking about. Okay. So now the weight of T prime will be weight of tree T plus weight of CD age that I have added minus weight of EL prime. Now I know that weight of CD is less than weight of E prime. That means this quantity is less than 0. It means it is negative. This implies that weight of T prime is less than weight of T. This is a contradiction. This is a contradiction because T prime is a spanning tree which whose weight is less than T, less than weight of T. Now let's see why this is a contradiction. I assumed at the beginning that uh, T is a minimum spanning tree with minimum weight. I mean, when I say minimum spanning tree, what do I mean? Spanning tree with minimum weight. That is why we call it minimum spanning tree. Now, I assumed at the beginning that this HCD is not there in T. So I have constructed another spanning tree T prime. Here T prime is T union CD minus CL prime. And what happened? The thing that happened is the weight of T prime turned out to be strictly less than weight of T. This is wrong. This is a contradiction. Why? Because I have constructed a spanning tree whose weight is less than minimum spanning tree. Right? This is not possible. By the definition of minimum spanning tree, any spanning tree that you will construct in my graph G, its weight should be at least as much as the weight of minimum spanning tree. But here, if you see in this red box, weight of T prime was less than weight of T. That means I have constructed another spanning tree whose weight is less than T, which is not possible because by definition, T is a minimum spanning tree. Okay. So that's why this is a contradiction. And this is a contradiction that means my assumption was wrong. And my assumption was CD does not belongs to ET. And since the assumption is wrong, what does that mean? That means CD belongs to T, any minimum spanning tree, right? Um Yes. So if you have any doubts, please ask. This is a bit so a sort of longer, like long proof relatively to the other questions. So if you have any doubt, I'll just let you stare at the proof for a minute. And if you have any doubts, please ask me. So, so here is the thing. I think some of you already explained why this should be I mean, why CD should be there. Because I think I didn't see who said. He said that if I add the minimum spanning tree, I can remove something else and keep it outside. Then I construct a new spanning tree whose weight is even less. I'm just writing the same idea down, but I'm just writing it formally. Okay, how do I find this edge whose weight is more than weight of CD? Once I remove it, it should be a tree. It should be acyclic. It should contain all vertices. It is connected. So this is just a formal proof, but I think some of you already got the idea right. So if for the rest of you, if you have any question in the proof, please ask. Otherwise, I'll move to the next question.
So, would such a argument be valid for the second minimum as well?
Second minimum as well. So what do you think? Will it be? So for the rest of you as well. So here I said that CD is always part of minimum spanning tree, right? What about second minimum? Will it always be there?
Yes,
Okay. Uh, what about third minimum? Will it always be there?
yes,
No.
but they are
Yeah.
distinct, right?
Wait.
Uh,
So let me get down. Let me explain this. So there is a very this is a trick. So this proof will only go through if you are talking about minimum weight age or second minimum. For third minimum, it will be false, because let me give you an example. So sorry, let me just write it down. So let's say here is my graph G, right? What is Can you construct a minimum spanning tree? There is only one. So let me write down this vertices first, and then there is T. So what edge can be there? AB will be there, because we just proved that any minimum spanning tree will always contain edge with minimum weight, given that all the edge weights are distinct. Okay, this is very important. I have to assume that edge weights are distinct, otherwise I cannot make such statement. So here the graph G that I have drawn, clearly all the edge weights are distinct. That means AB is there. Now let's just construct one. So after AB, I'll add AC, age is 2, and then I have 4. What is the third minimum age weight? It is 3. But is it there? No. Right? Why not? Because once I added BC, it formed an age with some cycles. So once I add BC in this tree T, you get a cycle. Not only that, the thing is that all the other edges in this cycle have weight strictly less than this age BC here. So what I'm saying is, if you add this age BC here, what is happening? First of all, you are getting a cycle. Then you can argue, okay, why not remove some why not remove some other age in cycle and keep BC there? The problem is that if you add BC, you have to remove some age, because the number of edges should be n minus 1. You are adding something, that means you have to remove something, the graph G, this T. But the problem is that when I'm going to remove the edges, what if all the edge weights are strictly less than what I'm adding? Then I cannot remove it, because I will get larger weight. Therefore, the idea of this proof cannot be applied for third minimum, fourth minimum, fifth minimum, any minimum. Only the smallest, like the minimum one. And for second minimum one also it is possible, because you can see I mean, once you add the second age, there cannot be a cycle, right? You added the first one, and then you are adding the second one. Two ages cannot form a cycle. You need at least three. Therefore, from the third point, it is not true that the age weight with third minimum weight, fourth minimum weight will always be there in my tree, minimum spanning tree. Okay. So if you have understood, please put +1. If not, please ask questions. Okay, I see +2 +1 3. Okay, great. Nice, nice. Okay. So let me give you a question. Okay, so okay, so wait, let me just see. Okay, so we have 15 minutes, so we can do one more question quickly. Um, so G has a so okay, so sorry, just let me write it down. So B statement is that uh, G has a an unique minimum spanning tree. Okay, so basically assume that you have given a graph G where all the edge weights are distinct. Now, is it true that G has an unique minimum spanning tree? So you have to first tell me whether it is true or false. If you think this is true, give me some idea of as to why. And if you think it is false, give me some counter example. So age weights are distinct. Age weights are distinct. This is given. So the question was here. So this is given distinct weight. So I'm just writing that observation down here. Age weights are distinct. So you can think for a minute or a couple of minutes and let me know. I think some of you have answered. So I'll give you a minute for others to think. Okay, so I think okay, so there are four true answers. So is there anyone who thinks this is false?
I do not have any proof, and neither I can think of a proof. But I think that 3 plus 4 is equal to 7, and 2 plus 5 is also equals to 7. So even if the weights are distinct, that quite possible we may have an alternative path which maintain the connectivity and come out with the same final weight.
Okay, okay. So this you okay. So what he's saying is, let me just explain to you the others. So I said G has a unique minimum spanning tree if the given graph has edge weights distinct. What he is saying, okay, maybe it could happen that I added two edges with one weight 1 and the other weight 4, so the total weight is 5. Maybe these two edges are not there. I added another two edges whose weight is 2 and 3. So I again get tree of size 5, weight 5. In that case, it could happen that I have two distinct minimum spanning trees. What do you think? Is this correct or this will never happen? Um, so if you think what is said could happen, then can you put +1? And if you think this will never happen, put -1. So I need some poll here so that I know you are listening to me. Okay, so there is one -1 at least. Uh, okay, so I think the rest of you maybe is not following what we did. So let me just
I have a different argument. I really didn't hear this one, I was thinking that in the upper one, with like there is, since they are also distinct, the edges are distinct. Therefore, for like two, for minimum and second minimum, they will follow a path, right? Like two edges, and after that, it may. You gave a contradiction in a question with triangles, I think.
Yes, so that was distance. Let me go back. Yes, so here. So the distances were distinct when in graph G and minimum spanning tree T.
So like after like some point of time, the graph can follow this kind of thing, and if this will become false.
Okay, this is also interesting. Okay, so I think I would have discussed it a little bit more, but I need to give you the answer because we are running out of time. The answer for this question is again true. There will be a unique minimum spanning tree, and I will prove it. Okay, like he said, it could happen that I have two edges with weight 1, 4, and two different edges with weight 2 and 3, and they form a minimum spanning tree. This will not happen. Okay, so let me prove it. Uh, okay, so let me ask you a question. If you have distinct edge weights and you started running Kruskal's algorithm on it, will it give me a unique minimum spanning tree? So the question is this: uh, you have given a graph G where the age weights are distinct. So what you decided to do is let's run a Kruskal's algorithm on this graph G. My question is, will Kruskal's algorithm always return only one minimum spanning tree?
Yes,
Yes.
Kuskal will return only one,
Okay.
and Kuskal will return only one.
Yes, yes.
And
No,
moreover, the prims will also return only one, subject to the selection of the first vertex.
yes. Okay. So at least this much part is correct. So you can sort of see. So I'm just trying to give you the intuition. I will prove it formally. In a Kruskal's algorithm, what happened? You have to put the edges in increasing order or non-decreasing order. But since the edge weights are distinct, this order of edges is unique, right? Because all the edge weights are distinct, I cannot have two different sorting of edges. The edge weights are distinct. That means the increasing order of edge weights will be unique. That means this sorting will be unique. And then the next part of Kruskal's algorithm is just to add the edge to graph, add the edge to solution, and check if it is forming a cycle. So no matter how you do it, Kruskal's algorithm will always return only one unique minimum spanning tree. Okay. So now what I will prove is the following. So let's say, so we know that in this case, Kruskal's algorithm will return a minimum, and unique minimum spanning tree T. So let's do this. So let's assume that unique minimum spanning tree returned by Kruskal's algorithm is unique. Kruskal's algorithm returned me a minimum spanning tree T. Now you might say, okay, I have some different algorithm for a minimum spanning tree, let's say prims or something else, and it returned a minimum spanning tree T prime where T and T prime are not the same. Then what could go wrong, right? So let's, this is again a proof by contradiction. So let's say there exists there exists a minimum spanning tree T prime such that T and T prime are distinct. Okay, so I'm proving this by contradiction. Okay, so this is very important when I say proof by contradiction, that means I will assume something opposite to what I have to prove. I have to show that there is a unique minimum spanning tree. I am saying something opposite. I am saying, okay, there is another minimum spanning tree T prime such that T and T prime are different. Okay, so I have assumed something opposite. Okay. Uh, okay, so what will we do? So let's say here is a sorted order of edges in with increasing weight. Let's say E1, E2, E3, EM, right? So what does Kruskal's algorithm do? It will sort the edges in the order in the increasing weight order because the all weights are distinct. So E1, E2, E3, EM. Okay. Now, so now let's say, okay, is it true that E1 will always be inside T? So my question is, if this is a sequence, which is an increasing order of weight of these edges, and T is a minimum spanning tree returned by Kruskal's algorithm, is it true that E1 will always be there? Yes, right? So someone say yes, because E1 is an edge, right, right. Yes, because we just proved that if edge weights are distinct, E1 is an edge with minimum weight, so it should be there in T. Not only in T, it should be there in T prime as well, right? So E1, sorry, E1 belongs to edges of T, and sorry, E1 also belongs to the edges of T prime, right? Because E1 is an edge with minimum weight, it is there in all minimum spanning trees, no matter which will you give me. So here we have two, T and T prime. So E1 is there in both of them. Okay. Then someone said E2 will always be there. Yes, E2 will always be there, and E2 because of the same idea. Okay, I'm not repeating the entire proof here. Now, here is the thing. So let's focus. Okay, this is a main argument. So what I will say is, okay, I have a sequence E1, E2, E3 up to EM. E1 is there in both the parts. Okay, I'm okay with it. E1 is there in T1, T and T prime. Let's move to E2. I ask this question, is it there in both of them? Okay, someone says, okay, both of them it is there. So E2 is there in uh, T and T prime. So okay, then I'll go and see E3. I will ask the same question, is E3 there in both T and T prime? The answer could be no for both of them, yes for both of them, or it could be yes for one of them and no for one of them. So what I'll do is I'll take the first edge in this sequence such that the EIth edge is there in T, but it is not there in T prime. Okay, let me write down this so you understand. Let's say EI is an edge that is in T but not T prime for smallest I. Okay, so let's sparse this one statement and you will be done with the proof. How I'm choosing the edge EI is the crux of this proof. Okay, how am I choosing? I'm saying ask this question whether E1 is in both of them. Yes. Okay, let's move to the next one. Is E2 in both of them? Yes. Let's move to the next one. Is E3 in both of them? Maybe no for both of, maybe the answer is no for T and T prime. So I move to the next one. Is E4 in both of them? The answer could be yes. Maybe okay, so both of them are there. Then maybe I went to E5 and then I observed E5 is there in T, but E5 is not there in T prime. Then E5 is the edge I'm interested in. So here I'm just denoting it by EI, saying that EI is the first edge in this sequence which is there inside T, but it is not there in T prime, right? And such an edge should be there because if all the edges in T are there in T prime, then T and T prime are same. That's what I have to show, that T and T prime are exactly the same. So just to make it interesting, I'm saying, okay, there is an edge in T which is there in T, but it is not there in T prime. Out of all such edges which are there in T, but not there in T prime, I'm choosing the one which is comes first in this sequence. Okay. So if you have understood how am I choosing EI, please put +1. Otherwise, I can explain you again.
So does this mean that if EI is the first stage wherein the violation happens, so then the edges say E1 to EI minus 1 are of no use?
No, 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 no.
Okay.
So okay, so let me say this. Like you said, EI is the first stage in this sequence where it happens that this edge is there in T, but not in T prime. What does that mean is any edge that appears before EI, like E1, E2, E3 dot dot EI minus 1, either that edge EI minus 1 or anything, either it is there in both of them or none of them. Sort of these two sets T and T prime agree with each other before I get to EI.
Oh,
This is the first time I'm violating this inequality, saying that okay, EI is there in T, but it is not there in T prime. Okay.
yes,
Okay.
yes.
Okay. Now let's see if this is the case, then something will go wrong, which I will tell you. Okay. So let's consider E double prime is T prime union EI and T. Okay. So let's consider this only for now. Now I know EI is an edge which is not there in T prime. So I say, okay, take that edge EI and add it to T prime. Just like we did before in the previous question, since I'm adding an edge to a tree, there will be a cycle, right? So there will be a cycle in T double prime containing EI. Okay. Can we say something about the weights of the edges that are appearing in this cycle, that are appearing in this cycle? Okay, so we are just two steps away from the final argument. Okay, so what I'm saying is you had EI which was not there in T prime, so you added EI to T prime. There will be a cycle because T prime was a tree and I'm adding an edge, so there is a cycle. Now let's look at the edges of that cycle. Okay, let's look at the edges of that cycle. It contains EI for sure. Can I say that this cycle will always contain at least one edge whose weight is at least, I mean, more than EI, right? So can I say that this cycle here, so can I say that the cycle that is formed in T double prime after adding EI will always contain an edge whose weight is more than EI? Can I say this? You can sort of think. So what do you think? Will there be always such edge with weight more than EI?
How can we make such an argument? Quite possible that T dash might be constructed in altogether a different way, and the dynamics of the network could be entirely different.
Yes, yes. So let me tell you. That's why the way I have chosen EI matters in this proof. The way I have chosen EI, that EI is the first stage that appears in this sequence such that EI is there in T, but EI is not there in T prime. Okay, that means what I'm saying is, so let's say this is E1, E2, EI minus 1. This is
Oh
EI.
yes, oh yes, yes. I understood because this is a sorted list. See a short-term list, yes. So therefore, I mean, this will definitely, I mean, true, and such an edge will definitely exist whose weight will be greater than EI. Yeah.
Okay, but let's see why. This is very important. When I added EI, this is in T, but it is not there in T prime. For the rest of them, which are here, this is true. This is in T, this is in T, this is in T, sorry, this is in T, T prime. Either this age is not there in both of them, or it is both of, I mean, it is there in both of them. So something like this. So this is the first time something like this happened. Now, what you have to ask yourself is EI picked the age T, sorry, Kruskal's algorithm picked the age EI and added to T. That means EI does not form a cycle with only these edges, right? How the Kruskal's algorithm choose age? It chooses EI. It sort of looked at EI and asked, okay, add EI to my minimum spanning tree, and ask, okay, is there a cycle after adding EI? If the answer is yes, then EI should have been not there inside tree T, because T is a minimum spanning tree that is generated by Kruskal's algorithm. That means EI cannot form cycle with the edges which are coming from here both in T and T prime. This implies that cycle in T double prime will contain an edge EJ which appears after EI in that sequence, in the above sequence. And since this is the sorted list, weight of EI should be less than weight of EJ. So what I can do is I can construct another minimum spanning tree T prime, which is T prime union EI minus EJ. And then I can say that weight of T double triple prime is weight of T prime plus weight of EI minus weight of EJ. But weight of EI is less than weight of EJ because that was a sorted list. So this is 0. That means weight of this newly constructed T triple prime is strictly less than weight of T prime, which means that I was able to construct a minimum spanning tree T triple prime whose weight is strictly less than T prime. This is not possible because T prime is a minimum spanning tree. There is no spanning tree whose weight is strictly less than T prime. This is a contradiction. That means our assumption was that there exists an age EI which is in T but not there in T prime. This assumption is wrong. There is no such age. That means T and T prime have same set of edges. That means no matter how you construct your minimum spanning tree, it will always be the same as outputted by Kruskal's algorithm. And I know Kruskal's algorithm will always give me only one minimum spanning tree.
How did we reach to the contradiction then? Can you
So
elaborate that part? Yeah.
yeah, so I constructed a tree T triple prime, which was
Mhm.
the which was I took my tree T prime, which was not the Kruskal's algorithm tree, some different that I have assumed first here,
Mhm.
T prime. All right,
Mhm.
and then
Mhm.
in this new tree T prime, I added EI, which was there in Kruskal's algorithm, but it was not there in T prime. I added EI and I removed EJ, which was the age with weight larger than EI, which was there in that cycle. And such an age exists because the Kruskal's algorithm chose EI to put it in the solution. That means EI had no age with ages that are appearing before EI. That means there is an age after EI which is there, which is forming a cycle. That means there is an age EJ with higher weight. So I just removed EI and added EJ. Sorry, removed EJ and added EI, and therefore I was able to construct another minimum spanning tree whose weight is less than T prime. But this is a contradiction because T prime is a MST. So T triple prime should not exist.
Yes, and here we are overly using Kruskal's algorithm and the correctness of the Kruskal's algorithm. So, what's the guarantee that if we exclude the EJ from here and instead of EJ, if we include EI, then everything would remain the same, the connectivity would still be maintained?
No, see, wait. Yes. This is a good question. When I removed EJ and I added EI, but you have to see that I'm removing an edge from the cycle. That means the graph cannot get disconnected. That's first observation. Second observation is that number of edges is equal because I'm removing edge and then adding an edge. That means it is also a spanning tree. So this newly constructed graph T triple prime is connected. It is spanning graph. That means it is a spanning tree. And not only that, if I look at the weight, it is less than the weight of T prime.
So we have removed EJ from a cycle means that, I mean, so where do we have this T double prime in the picture? Because here in this equation we have a T prime and a T triple prime. So what's the relevance of the T double prime then?
Oh, sorry. Wait. I define T double prime as T prime union EI. So here is the thing. T prime is a MST I have took uh, in the beginning, and I have found the edge EI. It is not there in T prime, but it is there in the tree generated by Kruskal's algorithm. Then what I said is that EI is an edge that is not in T prime. So let's add it inside it. Once I added it, it was a tree before. Now I am adding one more edge. That means there will be a cycle. In this cycle, there will exist an edge whose weight should be more than EI because EI is there in Kruskal's algorithm, the solution generated by Kruskal's algorithm. And EI only gets added to the solution if it doesn't form a cycle with edges that are appearing before EI. So the choice of Kruskal's algorithm has a reason behind choosing EI to put it inside the solution. It doesn't form any cycle with edges before that are appearing before EI and there are there. Um, is it
Yes. It's clear. Yeah, it's
okay?
clear. I understood. After writing this thing, now the things became clear when you wrote T double prime is equal to this stuff here.
Okay. Great. Okay, so is there anyone who has any doubt? You can ask. Uh, or else I think we are already 15 minutes above the time. So okay, so let me check. Okay, so there is no doubt in the chat, so I'll stop. Okay, so goodbye then. Oh, okay, somebody has a query. Okay, so you can ask it.
गुड इवनिंग सर सर वो सर इनरोलमेंट की डेट सर थोड़ी एक्सटेंड हो सकती है
I'm not in control of that. मतलब मुझे नहीं पता कि ये सब मैं बस टीए हूँ तो मुझे बस
सर एक्चुअली ना सर मैं मेल भी कर रहा हूँ कांटेक्ट भी कर रहा हूँ सर तो कुछ रिस्पॉन्ड नहीं आ रहा मेरे को वापस ना
तो ये एनपीटीएल जो लोग हैं उनका कुछ सपोर्टिंग ईमेल आईडी नहीं है क्या nptel डॉट सपोर्ट ऐसा कुछ आई
ओ
थिंक
यस सर है सर
हाँ तो तुम उस पे मेल कर सकते हो क्योंकि मुझे तो कुछ आइडिया नहीं है क्योंकि ये सारी चीजें आईआईटी मद्रास में होती है इनरोलमेंट ये सब और मैं अभी पुणे में हूँ तो आई हैव नो
अच्छा
आइडिया या
अच्छा सर तो सर आप अपने बिहाफ पे नहीं करवा सकते जैसा कुछ
नहीं मेरे हाथ में ये सब नहीं है आई एम नॉट आई मीन इंस्ट्रक्टर फॉर दिस कोर्स आई एम
या
ओनली
सर
टीए सो नो
ओके ओके सर ओके सर थैंक यू
थैंक यू या वेलकम ओके देन बाय एवरीवन